Hello, guys. Yeah, welcome you all. So our topic for today is virtual memory. So let's dive deep into virtual memory. Let's see what actually is virtual memory, and how virtual memory can be implemented, and let's see what is thrashing at the end. So okay, let's start today's session. So yeah, so what basically is virtual memory? Let's say, for example, we have a process of size 2 GB, and we have a main memory of size 1 GB. See, everything which needs to be executed should be brought to main memory, because CPU is the one which executes the process and the program. It should be brought to main memory. If a main memory size is smaller than the process size, then how to execute the process? So here virtual memory comes into the picture. So virtual memory provides illusion to the programmer that even though process size is much bigger than the main memory size, it can be easily executed. Okay, virtual memory is not a memory, it's just an illusion. It's not a real memory. It's implemented with the help of an hard disk or a secondary memory. It's an extension to the it acts as an extension to the primary memory, basically. Yeah, before getting into in how virtual memory is implemented, we should know why we are using virtual memory. Even though there are many concepts like paging, multi-level paging, simple paging, virtual memory is recently used in all the systems nowadays. So we should know why what is the exact use of the virtual memory. See, what we are doing in a simple level paging, uh, the processes are generally divided into pages. Okay, and the main memory is generally divided into frames. We place each page of a process in a frame of a main memory, so that our page size should be similar to the frame size. Okay, to keep a track of that particular thing, we use something known as page table keeps a track of holding up, so which page is placed in a which frame. You can see here a page 0. This is an example of an page table. A general example: page 0 is placed in frame 3. Page 1, these are page numbers, and these are corresponding frame numbers in which they are placed. Page 1 is placed in page 2 frame 2, and page 2 is placed in frame 6, etc. So we keep track of this. So even this page table is also placed in a main memory. So effective memory access time for paging is 2 into main memory access time. You can see here, this is the formula for effective memory access time for paging. One memory access is required to find the page table, and another memory for to find a particular frame inside the page table. Let's say we search where is this whole page table will be placed inside the one of the frame in the main memory. To find that, we need one memory access time, and let's say we are searching for frame 2. To find this frame 2, we need another memory access time, so we need two into memory access time to find that for simple level paging. So now let's see what is the main difference between simple level paging and virtual memory. In simple level paging, every page of a process is placed in one or the another frame of a main memory. Okay, entire process is placed inside the main memory. I mean, entire process, every pages inside the process are placed in the main memory. Whereas in virtual memory, not every page of a process is brought to a main memory. A part of pages or a required demanded pages are brought from the secondary memory to the main memory. Let's say, for example, CPU generates a CPU request for a page 3, for example. So we simultaneously bring page 2 and page 4 also to the main memory from the secondary memory. This concept is called locality of reference. We bring nearby pages, so that the CPU might demand for the nearby pages in the next time. We bring them from the secondary memory to the main memory. So this is called locality of reference. Okay, so now let's see the implementation of virtual memory. Virtual memory can be implemented using demand paging or demand segmentation, as you can see here, as I've told you earlier. So let's see how demand paging exactly works now. So yeah, this is implementation of virtual memory using demand paging. So initially, CPU generates an address. Address generated by the CPU is called a logical address or virtual address. and that virtual address needs to be converted to a physical address. The unit which converts logical address to physical address is called MMU, that is Memory Management Unit. It is responsible to convert a logical address into physical address. Okay, let's say initially CPU request for a page one. For example, let's take for page one. That request will be sent to a page table. We look in this is a page table I've told you earlier in simple level paging, the same page table. The page table contain two parts, that is frame number, and there are other bits also, that is such as p bit, that is present or absent bit, and dirty bit also. There are many other bits present. So for this we'll make use of p bit. So if a CPU requests for a page one, that if that page is not present inside the page table, we say it has page fault, because the requested page is not present in the main memory. Basically, if the requested page is present inside the main memory, is that is directly redirected to the main memory and search for the corresponding frame inside the main memory. If it is not present, let's say if it is requesting for a page one, the one is not present, so the p bit is zero, present or absent bit. This is generally present or absent. If the page is present inside the main memory, the p bit is 1. If a page is not present, the p bit is 0. Now the page 2, for example, page 0 is present in frame 2. Okay, so the p bit is 1. You can see a frame 2 is green in color, and page 0 is absent in the main memory, so the p bit is 0. Okay, that when the p bit is 0, there is a trap generated, or an interrupt is generated. Interrupt is an external signal stimuli which is generated, which so that user mode gets converted into kernel mode, so that operating system triggers uh, to solve that particular interrupt, and that request will be handled by the operating system. So here operating system goes in search of that particular page inside the logical address space. What is logical address space? So collection of all logical addresses generated by the CPU is called logical address space. This is generally an hard disk where all the process and corresponding pages are present. So in search of page 1, the OS goes to logical address space and brings this particular page 1 to the main memory. If the frames are freely present inside the main memory, it brings inside the main memory. If a frames are fully occupied in the main memory, then we use something known as page replacement policy. There are many algorithms such as FIFO, page replacement policy, and LRU, least recently used page replacement policy, etc. So we make use of page replacement policy algorithms to uh, place that particular page inside the particular frame. Let's say in our example we have many other free frames, such as frame 0, frame 1, frame 3. These are all free because they're not occupied by any pages. We place this particular page 1 in frame 3. So as and when we place inside the main memory, we update the page table. The p bit, basically the p bit inside the page table, from 0 to 1, because now here we have placed, right. Let me write it. So yeah, we have now got that particular page 1 from the LAS, and we have placed inside the frame 3, so the corresponding frame number is 3, and the p bit changes from 0 to 1, because now it is present. If you forget or don't update the page table, then again page fault will occur. Okay, so yeah, this fifth step is called updation step, and then that corresponding physical address which is converted, it is given back to the CPU. So to perform all these six steps, the time taken to perform all the six steps is called page fault service time. Okay, step 1 is here, step 2, step 3, 4, 5, and 6. To complete all this, time required is called page fault service time. So yeah, let's see how effective memory access is calculated inside in virtual memory. So yeah, you can see here effective memory access time equal to p is a probability, probability of occurring of page fault. Okay, probability that page fault occurs. And ps is a page fault service time, that is 1 to 6, the steps which I've just showed you, plus 1 minus p is an hit. Okay, if page fault, page hit, probability that one p is a page fault is 1 minus p is a page hit. Okay, m is the main memory access time. So this is a formula for effective memory access time in demand virtual memory using demand paging. Now let's see what are advantages and disadvantages of virtual memory. Basically, virtual memory has like quite a few advantages. Even though the size of a process is greater than the main memory, it can be executed. This is one of the major advantages of virtual memory. And and the disadvantage is it requires a lot of time to implement virtual memory because we are playing with the secondary memory and hard disk. If you ask me which is better in terms of simple level paging or virtual memory, I would say paging, because paging is, in paging we are dealing generally dealing with the main memory. Main memory is much faster as compared to the secondary memory. Virtual memory is time consuming because of page fault service time. We have to reduce this page fault basically. If you reduce this page fault, we can use virtual memory. um, to reduce this page fault, we should use better algorithms, page replacement algorithms, such as, for example, FIFO. If you're using FIFO page replacement algorithm, page replacement policy, page fault rate may increase, but using LRU, page fault may decrease. Okay, so LRU is better when compared to FIFO. So yeah, so we have to use better algorithms to reduce the page fault service time. So yeah, these are some of advantages and disadvantages of virtual memory. Another one big advantage is it increases the degree of multiprogramming. Or what this means is that increasing more number of process, bringing more number of process from secondary memory to the main memory increases the degree of multiprogramming, so that always the CPU will be busy executing one or the other process. Okay, now let's see what is thrashing. When degree of multi, you can see in this graph, when degree of multiprogramming is low, the CPU utilization is also low. After a certain point L, let's say L is a lambda, after a certain value lambda, uh, even though the degree of multiprogramming is more, the CPU utilization drastically decreases. This decrease in CPU utilization is called thrashing. When the system is in thrashing, it tends to hang, or uh, it stops working. The system basically stops working because of uh, decrease in CPU utilization. At this time, it basically the CPU will be doing the page fault service rather than doing executing the instruction. Okay, so how to remove or how to reduce this thrashing? So it can be, there are three ways to reduce this thrashing. First one is increasing main memory size. If you increase main memory size, the page fault will decrease, drastically decrease, and then more number of process can be executed. So thrashing also decreases. Second type is bringing, so decreasing degree of multiprogramming. If we close some, let's say, if for example, if you open more number of applications in a computer, sometimes our computer hangs. Okay, so if we close some of them, it'll get back to its normal state. So if we reduce the degree of multiprogramming, and CPU utilization increases. Okay, so this is one of the method. And the last is we should decrease, okay, long-term schedulers. These long-term schedulers bring more number of process into ready state. By decreasing the number of long-term schedulers, we can remove or decrease thrashing. Okay, these are some of the ways to reduce thrashing. So yeah, that's all for this video. Please like and share, subscribe to the YouTube channel. Thank you.